So our last speaker of the session is Olga Okrut, and she's speaking on behalf of the Dark Star Quantum Lab, which is a very interesting, nice name. Yeah, so she's talking about calculating the Nash equilibrium on quantum annealers. Olga, the stage is yours.
Thank you for the introduction. So hello everyone. So first of all, let me say thank you to the QWorld Quantum Science Days for an opportunity to present today. And I'm Olga Okrut, a quantum computation research Dark Star Quantum Lab. And today I would like to present on behalf of the team of Dark Star Quantum Lab. So we are a team of creative professionals tackling challenging problems that are challenged to solve on conventional computers. So, and as you may aware, many professionals in the area of quantum computation a bit of skeptical about current stage of quantum hardware and its usefulness. So yet we want to show quantum of advantage, so meaning delivering marginal but meaningful improvements in the near term. So today I would like to talk about the concept of Nash equilibrium and solutions on simulated annealing, as well as solutions on the physical D-wave quantum annealers. So let me start with a brief introduction to the Nash equilibrium. So the concept of Nash equilibrium is named after its inventor, the Nobel Memorial Prize winner in economic sciences, John Nash. Although the concept is part of the game theory, it finds its wide application in a variety of studies, such as economics, stock market, politics, or even in the evolutionary biology or in behavioral sciences. So the concept of Nash equilibrium is a concept within game theory, saying that the optional outcome of a game is the outcome where no player has an incentive to deviate from their chosen strategy. So Nash equilibrium can be thought of as a decision-making theorem, which attempts to determine mathematically and logically the actions that participants of the game should take to secure their best outcomes for themselves. So in this case, if a strategy of a player is in a Nash equilibrium and this player for some reasons decides to deviate from their chosen strategy, they will receive a poorer outcome. So the outcome here can be thought of as the money, some points of satisfaction, some happiness. And depending on the game, there can exist many Nash equilibria or not at all. So some examples of the Nash equilibrium can be mutually assured destructions of the Cold War era. So in fact, the recent Indian-Pakistan MID in the nuclear weapons is also an example of the Nash equilibrium. From the economics and finance, strategies, trading and bargaining also part of the solution of Nash equilibrium. And Nash equilibrium also describes biology, evolutionary biology, and some cases in a behavioral science. So the problem of the Nash equilibrium for, let's say the small problem for two players seems to be easy enough to solve on the conventional computers. So nevertheless, as the number of players and strategies increase, the problems becomes NP-complete in a pure strategies. So it is impossible to find Nash equilibrium using simple algorithm, such as iteration, stochastic algorithm, or simple brute forms that are mainly used to approach the problem. So these algorithms are good for small games, but for the larger games, they will fail or they will just provide an estimation of the Nash equilibrium points. So saying this, finding Nash equilibrium points requires a revision of existing approaches and the development of a new algorithm. In our work, we aim to find Nash equilibrium using quantum-inspired algorithm, that is simulated annealing and physical QPUs. And so the important to say here that the real quantum hardware utilizes the phenomena of quantum tunneling to reach a global minimum faster in comparison to the simulated annealing. So our goals were to formulate a problem of finding Nash equilibrium as a QUBO, quadratic unconstrained binary optimization. And secondly, we would like to test our formulation on a simulated annealing and later on the physical D-Waves hardware. So first of all, of course, one has to format the problem such that it matches Ising-Hamiltonian formulation, that is the underlying concept of the D-Waves quantum annealer. So in other words, we stated the problem as a quadratic unconstrained binary optimization by switching from the spin variables S sub i's to the binary variables X sub i's. So this reformulation allows us to search for Nash equilibrium points in pure strategies immediately with no extra post-processing later. So in general, so one is required to know the payoff matrices for each of the players in the game. So in my example, I will call those matrices M and N, and the variables of the strategies will be P and Q. And so then to calculate the payoffs for the player, we just multiply P transpose times M times Q for the first player, and for the second player, the payoff would be P transpose times N times Q. And of course, so in the problem of Nash equilibrium, we're interested to find the maximum total payoff for the both players in the games. And so just here, let me mention this. So of course, we formulated the Nash equilibrium as a QUBO problem for mixed strategy games, meaning that the strategies can be rational numbers, rational values, but so we will solve for binary given the recent limitations in the quantum hardware. So of course, the formulation of a Nash equilibrium problem is not full with missing constraints that we can add as a penalty terms to the QUBO. So the first constraints are relatively simple. They just say that each player must play one strategy only. So that is, a player cannot consider two different actions simultaneously. The second constraint arises under Kahn-Tucker constraint optimization theorem that ensures the existence of Nash equilibrium points in a game. So you can read about this theorem in our paper for more details. So gathering everything together and adding constraints as a penalty term, we obtain the general expression for the QUBO. So where the term in the purple box corresponds to a solution of an unconstrained counterpart, and the parts in the green and pink boxes are the constraints multiplied by corresponding penalty term multipliers. So since one cannot solve a problem as finding a global maximum on a quantum annealers, we can play a simple mathematical trick of minimizing the same objective function but with the opposite sign. So that is why the problem becomes a minimization problem and all the sign in the expressions are reversed. So as soon as we got the formulation of a problem as a QUBO, so the next step, of course, is to test our ideas as a simulated annealing and on a physical QPU. And so the next is basically the software engineering part. So one has to construct a QUBO matrix and construct the model. So in our research, we used binary quadratic model, BQM. But of course, depending on your vision, on your needs, you can try to use constrained quadratic model, CQM. So then you can add your constraints and the penalty terms together with penalty multipliers. Again, depending on the previous step, the constraints can be added in different ways, and you can find all of this information, how to define the model, how to set up constraints and penalty multipliers in the D-Waves tutorials and D-Waves documentation. Okay, so the next part was to submit as a simulated annealing, and that was relatively easy. So you just submit your simulated annealing sampler available through the D-Waves software package, and you will see your first results. So the things are a bit different for the real D-Waves quantum annealer. So prior to submitting to the physical QPUs, we have to undergo embedding into the D-Waves topological graphs. So in general, you can choose any available embedding algorithm on the D-Waves package, or you can implement the custom if you want. So for this, for our research, we used embedding composite. And so after running the experiment on the QPU, it is also nice to consider data post-processing, classical data post-processing, especially for a large number of strategies or for a large number of players. So this also helps you to narrow down your solutions and to get a better quality of results. So let me consider one of the examples you can find in our paper. So that is the battle of the sexes. For the scope of this presentation, I'm considering the simplest example, but you can find more sophisticated down the paper. So consider a couple, Adam and Beth, and they like to do something together, but one of them prefers to watch a soccer game, so that is Adam, and the other player likes ballet, so this is Beth. And so you can see here the payoff matrix for both players, and their payoffs depends on their choice of strategies and the strategy of their partner. So payoff in this example represents satisfaction. So how happy will both of them be if they will select a strategy. So for instance, if Adam goes to soccer and Beth goes to the ballet, both of them are unsatisfied with their choices of actions because they do something separate. So they will receive -1 to their satisfaction. However, if both of them go to a soccer, for example, then Adam is satisfied, he will receive +2 points to his satisfaction. Beth is also happy, she will receive +1 point to her satisfaction. So if you analyze the table, you can see that both players, so if both players go to the ballet, both players go to a soccer, so then they receive the maximum total payoff. So these 2 points we call Nash equilibrium and pure strategies. And so that's what we will try to find on the quantum-inspired algorithm and on the physical QPU. So for the given problem, so first you have to define your variables, your binary variables that represent strategies for both players. So those are PIs and QIs. And then you just need your payoff matrices for both of the players, so the points of satisfaction. And taking into account the objective function together with the penalty terms that I just defined in the previous slides, we can construct objective function for the battle of the sexes example. Again, so we want to maximize the total payoff, but since we cannot do this on the quantum annealers, so then we will minimize and we will consider everything with the opposite sign. So the objective function for this game will be with the opposite sign. So what were our results after the execution? So here you can see the results for the simulated annealing, D-Wave Advantage, and D-Wave 2000 Q6 QPUs. So we access the D-Waves hardware through AWS bracket services, and just a bit I will talk about this more. And so you can observe here 2 major peaks. So they exactly correspond to 2 Nash equilibrium points. So that is 0, 1 or 1, 0. And those points exactly mean that both of the players either go to a soccer game or go to a ballet. Yeah, so you can also see some minor peaks in the simulated annealing, but those are mainly represent the fact that the algorithm may sometimes stuck at local minimum during the execution. So the other questions that we were interested to confirm or not to confirm is some kind of speed up in finding Nash equilibrium points for larger problems. So in the table, you can observe a short summary on the algorithm execution as a simulated annealing on a conventional computer with an Intel Core i5 CPU and the latest graph topology QPU from D-Wave. So this is advantage for one QPU. So as you can see, the trends that for both of the columns, the time of the execution on classical machines increases with the increasing number in strategies. So that is, the execution time was around 0.6 seconds for 2 strategies games, however, increased to 15.4 seconds for 8 strategies games. So the interesting result is that the QPU time for all numbers of strategies remains under a second for the QPU. And we anticipate to see the same QPU time for the games that require up to 100 logical variables. However, so to our tiny disappointment, we have to admit that we observed a delay time from the AWS bracket of around 12 or 13 seconds. This delay is mainly caused by sending data to AWS and then receiving back the results. All right, so let me give some short conclusion. So in this research, we were able to format the problem of finding Nash equilibrium points in the QUBO format to execute as a simulated annealing and on the real quantum hardware represented by D-Wave quantum annealers. So we observed a speed up in the QPU time over the CPU, the classical unit of around 6 to 22 times, depending on the number of strategies. So the problems that are required to be submitted to a physical QPU, one has to undergo some additional process and additional data preparation, such as embedding and right choice of penalty multipliers. And of course, these preparations can significantly influence outcomes, such that as the number of Nash equilibrium points or quality of solutions. And for the games with a larger number of strategies, classical post-processing may be required to narrow down the best solutions for the problem. So, of course, we should admit that it was the first research done in finding Nash equilibrium points in pure strategies, and certainly this research has some further areas of improvements. So, for instance, it would be nice to solve Nash equilibrium for the mixed strategies games, so which is impossible right now due to the current limitations in quantum hardware. The classical quantum algorithm or hybrid approach could also enhance the outcomes in terms of performance and quality of solutions for problems with 50 or more strategies. So also solving for the games with 150 strategies. Sorry. So what I'm trying to say is that also would be nice to see the outcomes if we try to solve for games with 150 strategies. And of course, so some of you might be interested to see some performance comparison between the classical algorithms, such as iterations or stochastics algorithm, and the quantum-inspired algorithm. And of course, the finding and better embedding or custom embedding to the D-Wave's graph topology and further research in the penalty terms can allow to increase success rate in finding Nash equilibrium points. last but not least, so thank you for your attention, and any comments are welcome, and I can answer some questions.
Thank you, Olga. Thank you very much for the nice presentation. We actually have already a question in the chat here. Maybe you can also read it yourself. I read it out loud, but I think it might be hard to just hear. Okay, so with given assumption PQ representing only one strategy, i.e. a deterministic distribution, the problem lies in P, as it is enough to brute force all n times m solutions. Perhaps the problem becomes complicated with PQ being general distributions, which is then equivalent to solving quadratic program, which is in general NP hard. Is that, there was a question in the end. Is that correct?
Yeah. Yeah, I see. I see the question. This is actually a very good question, and so the thing is that there is a lot of debate still going on around the completeness of Nash equilibrium, and so of course it is NP hard for games in the mixed strategies. So when let's say each player will play one half this strategy and one half this strategy, so half of the time one strategy, half of the time the other strategy. But it becomes NP complete if we are talking about the pure strategy, so which represent the binary variables. So you can see this justification down the paper.
Okay, thanks. There was, I guess, a comment that there is a paper called...
Yeah, so so Dr. Faisal, that Dr. Faisal, my colleague, exactly cites the paper that provides more elaboration on this. Yes, as I said, there is still debate on this question, and you know, there is no established decision like, is it NP hard, is it NP complete, and how to consider this problem.
Okay, very good. So we have the reference here to we can look it up further. And Adam Gloss, who just posed a question, said thank you. So is there more questions from the audience? We have a bit of time left, I think. I actually have a question regarding, you compared the algorithm running on this D-Wave quantum computer to an Intel Core i5 or something. So I understand the concept of quantum supremacy when you say okay, even supercomputers cannot calculate it within the next million years. But how do you what led you to compare it to this like rather standard computer? Because I would assume, but I might be wrong, that a better computer, supercomputer, will beat the D-Wave in this particular task. So how do you, in this field, when you do these tests, how do you compare? How do you say, okay, because in your results you clearly see the advantage of the D-Wave here, but like I think it's yeah. How do you decide to that?
Yeah, that's a good question, and the reason for that is actually there is no available data, no available research to see if someone tried to solve this problem on the supercomputers. So we didn't find any, and so we cannot compare actually. So that's why we decided, okay, so probably, well, that's most likely, even for the supercomputers, that will be a very challenging task if we're talking about large problems. So probably that's the thing where the quantum computers can shine off and they can play a crucial role and solve this problem in a bit different way, but anyway, they will be able to solve it.
Okay, yeah, it boils down to the fact how, if you just make your problem harder, then of course at one point your Intel processor might not do that at all anymore.
No, it won't.
Okay, thank you. Yeah, so if there's no other questions also from Discord, and in the chat there's none.
Yeah, there is nothing. Yeah,
there's nothing. Good. So with this, I think we can thank all speakers again for this last session of this first day. Andrii, Zoltan, Shaeema, and Olga. Thank you very much. You did all a really nice talk. I enjoyed it a lot. And yeah.